Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to go over how to write balanced chemical equations from the word descriptions of these reactions. So let's get into this. So one of the things you want to look out for when you're translating sentences into balanced formulas, balanced equations, is you got to look for the key words, key phrases that indicate that something is a reactant or a product. What is the states of the matter? If you're able to determine that from the sentence or from the words or descriptions that they're giving you. If it's not there, then you may have to use your solubility rules or your solubility table in order to figure that out. So let's go ahead and go over this. So in the first sentence, we have the complete combustion. They want the balanced equation for the complete combustion of benzoic acid, and they give us the formula for benzoic acid. So complete combustion, you have to understand what combustion is. Combustion is burning. And so whenever you have combustion, you have to have oxygen as a reactant, oxygen gas as a reactant. That is necessary for combustion because when you're burning something, things burn only in the presence of oxygen. Take away the oxygen, it's not going to burn. So if you're told that something is undergoing combustion, you know that oxygen has to be one of the reactants along with whatever it is they're asking you to combust, right? So in this case, the benzoic acid is a reactant, the oxygen is a reactant as well, okay? So the other thing you want to keep in mind is this word complete. So complete combustion is important to know. That's going to distinguish it from incomplete combustion. So complete combustion is when you combust something in the presence of oxygen. If it is a hydrocarbon made up of carbon and hydrogen and oxygen, then you know that the only two products that are formed from complete combustion is carbon dioxide and water. So if it was incomplete combustion, then you get other byproducts, and so we want to avoid those. So it's really important that they indicated that it's complete combustion. So if it's complete combustion, the only products are carbon dioxide and water, assuming that you've got a compound, a reactant that only has carbon, hydrogen, and or oxygen in it. So if you got sulfur in there or nitrogen in your compound, then you might get nitrogen dioxide or sulfur dioxide as a product as well. But here we only have carbon, hydrogen, and oxygen. So let's write out the equation. So we're going to write out the skeletal equation. So we have C6H5COOH plus, and we got to have oxygen as a reactant. The thing you want to keep in mind is, especially when you're translated into formulas, you have to know your 7 diatomic elements, right? So to remember that, there is a nice mnemonic device, a sentence or phrase that you can use to help you remember what those 7 are. And that is, horses need oats for clear brown eyes. So those 7 words indicate the 7 diatomic elements. Horses, H, hydrogen, H2. Horses need, N, nitrogen. Oats, O, oxygen. 4, F, that's fluorine. Clear, Cl, chlorine. Brown, Br, bromine. Eyes, iodine. So horses need oats for clear brown eyes. If you can remember that sentence, then you can remember the 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, so we have oxygen, O2. There's 2 others that you may want to remember: phosphorus is typically a P4. So it exists as a molecule where there's 4 atoms bonded together, so P4. And then sulfur is commonly S8. So it's a ring structure with 8 sulfur atoms bonded together. So those might be important to remember as well. Okay, so I've got my 2 reactants, and I already know what the products are, carbon dioxide and water. And so now that I have this skeletal structure, now I have the balance equation and write the states of matter. And for the states of matter, oops. Sorry about that. So for the states of matter, since this is undergoing combustion, you burn stuff that are solids. You're not going to burn a liquid normally. Like if it's, this is benzoic acid. If it was in water, it would be aqueous, but you're not going to burn it in the aqueous form. So this is going to be a solid. Oxygen is going to be gas. CO2 is gas. And then water, if you're undergoing combustion, obviously there's heat, there's fire. Water is typically not going to be in the form of liquid water. It's going to most likely be in the form of vapor, so gaseous water. So best represented by a gas under combustion conditions. And then if you balance it, right, to balance the equation, you want to balance everything except for oxygen and hydrogen. And typically, if you have an element that's by itself as not part of a compound, then you would leave that for last. Here I have oxygen by itself. It's not part of a compound. So I'm going to leave oxygen for last. I'm going to balance the carbon first. So I have carbon here, 6 carbons here. I need 6 over here. I'm going to put a 6. Remember, when you balance a chemical equation, you only change the coefficients. Don't change subscripts. Don't ever change the formula. Once you got the formula the way it's supposed to be, don't change it. You're only going to change the coefficients in front of the formulas. So I've got 6 carbons there. So here I have 6 hydrogen, 5 here, 1 there, 6 hydrogen. Here I only have 2, so I need to put a 3 here because 3 times 2 is 6. And then finally the oxygen. Here I have 2, and here I have 2, that's 4. Here I have 6 times 2 is 12. So I'm going to put a 12 there. And here I have 3 times 1 is 3. So here I have a total of 15. Here I have 2. I don't really want to do anything with this because if I change this, if I put a coefficient here, then I change the carbons, I change the hydrogens. That's why we save this for last. So I want to add a coefficient that's going to help me balance the oxygens. So I know I have 2 oxygens here. So I need this number here to add to the 2 so that way I get 15. So I have a total of 15 on this side. So what plus 2, or so 2 plus what is going to give me 15? Well, that's 13, right? So I need 13 out of this. How can I make this 13? Well, you can use a fraction. Okay, so what times 2 gives me 13? That's going to be 6.5. So 6.5 or 6.5 is going to give me 13 oxygen. 6.5 times 2 gives me 13. 13 plus 2 gives me 15 on this side, which is going to be equal to the 15 on this side. I now have a balanced equation. It's balanced, right? Everyone would agree that it's balanced, but I can't use a fraction, or I can't keep a fraction in my finished balanced equation. So I want this to stay balanced. So I don't want to unbalance it, but I need to get rid of the fraction. One way you can get rid of the fraction is by multiplying by 2, right? I can get rid of a half by multiplying by 2. However, if I multiply this by 2, I have to multiply the whole equation by 2 in order to keep it balanced. So let's do that. So 1 times 2 is 2. 6.5 times 2 is 13. Six times 2 is 12. And 3 times 2 is 6. So now I have my balanced equation, and I've got all whole numbers for my coefficients. Okay, let's go to the next one. The decomposition by heating of solid mercury to nitrate to produce pure liquid mercury, nitrogen dioxide gas, and oxygen gas. So it's a decomposition reaction. So we know from decomposition reactions that you start with one thing and it breaks down into several things. So here the only reactant is going to be the mercury 2 nitrate, and we're told it's a solid. So let's go ahead and start with that. So we have mercury 2 nitrate. So the mercury 2, that's going to be Hg. So in this case, the Hg is going to have a 2 plus charge because it's got a Roman numeral 2. And nitrate has a negative 1 charge. Nitrate is NO3 minus. So I need 2 nitrates to balance the 2 plus charge on my mercury. So that's going to be NO3 2. And this is a solid. And that's going to break down into liquid mercury, pure liquid mercury. So that's going to be Hg liquid. Elements by themselves, unless it's one of those diatomic elements or phosphorus or sulfur, it's only going to exist as a single atom here, not as a molecule. So it's just Hg liquid plus we have nitrogen dioxide gas, NO2, plus oxygen gas. Again, oxygen is one of the diatomic elements, so it's O2, G for gas. Now, one of the things I forgot to mention is in order to write out balanced equations from the words, you need to know how to translate the words or names of compounds and elements into their formulas. So you've got to know how to name your ionic compounds. You got to know how to name your covalent compounds. You got to distinguish between those that have a Roman numeral, ionic compounds that don't have a Roman numeral, transition elements, which transition elements have a Roman numeral, which ones don't, right? Which main group elements have a Roman numeral, which don't. So remember, there's at least 5 exceptions, right? So lead and tin are not transition elements, but they do have Roman numerals because they will have multiple charges. Silver, cadmium, and zinc, they are transition elements, so you might expect them to have a Roman numeral, but they would be exceptions. They don't have a Roman numeral. Silver only ever has a +1 charge. It does have a +2 charge, but it's very, very rare, so we ignore it. If you have zinc, zinc has a 2+ charge, cadmium has a 2+ charge, and that's it. So you've got to know your nomenclature. You've got to know how to name your compounds so you can translate them to formulas. Okay, so here we have our skeletal equation. Now let's go ahead and balance it. So we always start with the metals first and then go to the nonmetals. And then when you're at the nonmetals, you want to balance every nonmetal except for oxygen and hydrogen. That's a rule of thumb, not always the case. It depends on other things like, do you have another element that is, by itself, right? And then there you kind of follow the rules as well. Like, so for example, if I have hydrogen by itself and not oxygen, then I would save hydrogen for last. If I had nitrogen by itself and not oxygen, then I would save nitrogen for last, right? What if you have two elements that are by themselves, like a metal and a nonmetal? Well, metals come first, so you would balance the metal first and then leave that nonmetal for last, right? What if you have two nonmetals, right? If you have two nonmetals and one of those is oxygen that's by itself, then balance the other nonmetal and keep oxygen for last. So you kind of follow the rules as they, generally speaking, but they pretty much work on these type of problems. So here I've got mercury is a metal, so I've got one here. And so after that, now I have nonmetals. So I'm going to balance, I only have nitrogen and oxygen left. So I'm going to balance nitrogen first and then oxygen. Because notice I have oxygen by itself, so save oxygen for last. So nitrogen, I have two nitrogens here. 2 times 1 is 2. So don't forget, if in order to figure out the total number of a certain atom in your formula, it's going to be the coefficient multiplied by the subscript. So here I have 1 nitrogen, 1. So 1 times 2 is 2. So I have 2 nitrogens on this side. Here I have 1 nitrogen. So I need a 2 here to get 2 nitrogens. So now my nitrogens are balanced. 3 times 2 is 6, or 1 times 3 times 2 is 6. So here I have 6 oxygens. Here I have 2 times 2 is 4. And then I have 2 here. That's going to be added together, and I have 6. So my oxygens are balanced. So I have a balanced equation now. Next, we have copper metal reacts with gaseous oxygen. So we're going to translate that. So copper metal is an element by itself. So this is going to be a single atom. It's not one of the diatomics. It's not a molecule. It's just a single atom. So I'm going to put Cu. And copper's a metal. It's going to be solid. The only liquid metal that we know of is mercury under room temperature, normal conditions. So this is going to be solid copper plus it reacts with gaseous oxygen. So it's telling us it's a gas. So O2, it's a diatomic element, O2. Carbon dioxide, so it's reacting with that as well. So CO2, and that's a gas. And water to form. And so water, we're not undergoing combustion, so we're assuming here that water is a liquid. H2O liquid. And that's going to form what? It's going to form green basic copper carbonate. And so here's our product. This is the only product we have. Cu2 OH2. CO2. So now that we have our skeletal structure, now we just balance the equation. Notice that I have oxygen by itself, so I'm going to save oxygen for last. I don't have any other, I do have an element. I have copper by itself. So here is an example where I have two elements by themselves. Well, which one do I save for last? We'll go back to the rule regarding metals versus nonmetals. Metals are balanced first before nonmetals. So I'm going to balance the copper first. I'm going to save oxygen for last. So here I have one metal, two coppers, one copper. So I need two on this side, so I'm going to put a 2 coefficient. So now my copper atoms are balanced. Now I can go to the nonmetals. So I have carbon, hydrogen, and oxygen left. I'm going to balance everything except for hydrogen and oxygen. And then once I get those two, then I'm going to balance the hydrogen before the oxygen because I have oxygen as an element by itself. So I'm going to save that for last. So carbon, I have one carbon here. I have one carbon there. It's already balanced. That was easy. Now for the hydrogen, I have two hydrogens here. And I have 2 times 1 is 2 times 1 is 2. So I have two hydrogens for here. So that's already balanced. This is getting easy. So now let's look at our oxygens. I have 4 oxygen on this side. 2 here, 2 there. Nope, and I have 1 here. So that's 5 oxygens total. So 2 plus 1 is 5. So I have 5 on this side. How many do I have on this side? So I have 2 times 1 is 2, right? And I have 2 on this side here. 2 times 1 is 2. So I have 2 oxygens here. I have 2 times 1, 2 oxygens here. So I have 4 oxygens. So I have 4 oxygen on this side, but I have 5 on this side. This can be kind of hard to balance if you don't use a fraction. But if I use a fraction with my O2 here, it becomes very simple. So I want 4 on this side. I want to get this side equal to this side. So this has 4. I have 5 on this side. I need to get rid of 1. So what could I do? So I have 2 here. I have 1 there. I have 3. Right? I have 3 in these. I need 1 more to make 4. How could I make this a 1? What times 2 equals 1? And if you said 1/2, you would be correct. So I could put a half here. 1/2 times 2 is 1. So I get 1 oxygen here, plus 2 is 3, plus 1 is 4. So I have 4 oxygens on this side. I have 4 oxygen on this side. It is balanced. But I can't keep the fraction. I have to get rid of the fraction. So this is a half. To get rid of half, I need to multiply by 2. But I need to multiply the whole equation by 2. Otherwise, I unbalance the equation. I want to keep the equation balanced. So 2 times 2 is 4. So I'm going to put 4 here. 1/2 times 2 is 1. So I'm just going to put that there, no coefficient except for the 1, it's there. 1 times 2 is 2. 1 times 2 is 2. And 1 times 2 is 2. And so now we have our balanced equation with no fractions. It's all lowest whole number ratios here. That's the way it's done. Finally, our last one. We have calcium dihydrogen phosphate. So we're going to write out the formula. So that's going to be calcium dihydrogen phosphate has a charge of a -1 on it. Calcium has a +2, so I need two ions of dihydrogen phosphate. Okay, that's going to react with sodium hydrogen carbonate or bicarbonate, sodium bicarbonate or sodium hydrogen carbonate and bicarbonate are the same things. So that's going to react with sodium hydrogen carbonate. That's going to be NaHCO3. So that's the formula for sodium hydrogen carbonate. And what is it going to produce? So the key word here is produce. So if you see a word like produce or forms or creates or anything like that, whatever follows is going to be product, right? So we have here reacts with. So reacts with indicates your reactants. So reacts with copper metal, reacts with gaseous oxygen, carbon dioxide, and water. So I knew that those were reactants because of reacts with. And then to form, right? To form means that whatever follows is product. So reacts with indicates reactants. To form indicates products. Same thing here. To produce, right? The word to produce indicates that whatever follows is going to be a product, right? So same thing here. Reacts with. Producing, right? Producing what? Tricalcium phosphate. Now, tricalcium phosphate is the same as calcium phosphate. The normal way of naming your ionic compound is we don't use prefixes for ionic compounds, but outside of science and chemistry, you might find it referred to as tricalcium phosphate. But the most common way of naming the substance is calcium phosphate. Same thing with dye here, sodium. Sodium hydrogen phosphate is the name of the substance, but outside of chemistry class, maybe in your recipe or your cookbook, you might see these like tricalcium phosphate, disodium. It might be written on the back of a label of a food package or a nutritional label or something like that. But it's written in parentheses to indicate that that's a possible name as well. But really, the right name is calcium phosphate for chemistry purposes. So that's going to form what? Tricalcium phosphate, or just calcium phosphate. And the formula for calcium phosphate is Ca3PO42 plus, and then sodium hydrogen phosphate, that's going to be, excuse me, Na sodium phosphate or sodium hydrogen phosphate. Hydrogen phosphate is going to be HPO4. So Na2HPO4. And then we have, where's the other one? Carbon dioxide and water. So carbon dioxide and water. I want to give myself some room here. So I'll put that down here. So carbon dioxide, I'll put that down here. CO2 plus H2O. So these are the four. Let me bring this down a little bit. There you go. So here's our two reactants, and they're giving us four products. This, by the way, is the main reaction that occurs in baking when you're baking cakes or breads or things like that, right? So this is your main reaction in that process. And so we need to balance this equation. We need to give the states of matter. So here, let's see. So since we're baking, this is going to be in the aqueous phase. So in order to get these two to react, they have to be dissolved in water, so that way the ions can come apart and start forming with each other. So this is going to be aqueous. So then these ions can come apart and form these products here. And so calcium phosphate, or which is the name calcium phosphate here. So calcium phosphate is actually going to be a solid if you look up the solubility rules. So most phosphates are going to be insoluble in water, and there's some notable exceptions, but calcium is not one of those exceptions. So that's going to be a solid, insoluble in water. So we have solid here. Sodium hydrogen phosphate, this is going to be soluble. This is aqueous. Sodium ions and sodium compounds are almost always soluble. So that's going to be aqueous. And then carbon dioxide, of course, is a gas. Water is going to be a liquid in this case. We are baking, but it's going to be a liquid. You might put gas there too. That might be acceptable. I'm going to put a liquid. Now here we have our equation. Now we're going to balance the equation. So again, the rule here, the rules I follow is metals before nonmetals. So I have 1 calcium here. I have 3 calciums here. So I'm going to put a 3 in front of the calcium. So that's balanced. Here I have 1 sodium. Here I have 2 sodiums. So I'm going to put a 2 in front of the sodium. So now that's balanced. And notice here I don't have any elements by themselves. So in this case, I'm just going to follow the rule of thumb, meaning that I'm going to balance all the nonmetals first, except for oxygen and hydrogen. And then when it comes to oxygen and hydrogen, I'm going to balance oxygen last. So typically you balance oxygen last, unless, of course, you have an element other than oxygen that's by itself. So then you would save that for last. But here I don't have any elements that are by themselves, so oxygen is going to be the default last element. So I have hydrogen here, phosphorus, oxygen, carbon. So I'm going to balance carbon and phosphorus first, and then I'll balance hydrogen and then oxygen last. So phosphorus, I have 3 times 1 times 2, right? So 3 times 1 is 3 times 2 is 6. So I have 6 phosphorus on this side. And over here, I have 1 times 1 times 2 is 2. So in order to make this 6, but you also have phosphorus over here, so you can't forget about that. So I have 2 phosphorus over here, and I have 1 phosphorus over here. So that's going to be 3. But I have 3 times 2 is 6. So I have 6. So I need 3 more on this side. So how can I do that? So I could do that by putting, let's see, I could put a 3 here, like so. That would give me 3 more. 3 times 1 is 3, plus the, actually that wouldn't work. Sorry, my bad. Oops. Sorry about that. All right, so I said 3, but then I realized that's not going to work. I need 4. So I'm going to put 4 here, right? So now 4 times 1 is 4, plus the 2 I have here. So 2 times 1 phosphorus, I have 2 phosphorus here. And then I have 4 times 1 is 4. 4 and 2 gives me 6. So that would balance with the 6 phosphorus I have here. So that's balanced. But I need to go back to my sodium. Now I change the sodium. I have 4 times 2 sodium. That's going to be 8 sodium. So I'm going to have 8 on this side. So I'm going to have to change this to an 8. So now I have 8 sodium. So now that's balanced. Okay, so sodium's balanced. My phosphorus is balanced. Calcium is balanced. Now I go to carbon. So carbon, I have 8 times 1 is 8. And I have 1 over here, so I need an 8 in front of my carbon. So now I have 8 carbons. So my carbons are balanced, my phosphorus is balanced, my calcium, my sodium, everything's balanced except for oxygen. So let's take a look at oxygen. So you're going to multiply the coefficients and the subscripts. So I have 3 times 4 times 2. So 3 times 4 is 12 times 2 is 24. So I have 24 oxygens from this one. Here I have 8 times 3. So 8 times 3 is 24. So I have another 24 oxygens there. So 24 times 24 is 48. So I have a total of 48 oxygens on this side. Well, how many do I have on this side? So I have 1 times 4 times 2. That's going to be 8. So I have 8 oxygens for that one. I have 4 times 4, which is 16. So I have 16 oxygens for that formula. 8 times 2 is 16. So I have 16 from my carbon dioxides. And here I have 1. So 1 times 1 is 1. Oh, you know what? I forgot the hydrogen. Let's make sure the hydrogens are balanced here. So here I have 3 times 2 is the hydrogen. That's 6. So I have 6 on this side. So 6 hydrogen for this one. And then 8 times 1 is 8. So I have 8 hydrogen here. So 6 and 8 gives me a total of 14. And so I need 14 hydrogen on this side. So I don't have hydrogen here. I have hydrogen here. So 4 times 1 is 4. So I have 4 hydrogen from here. No hydrogen here. And I have 2 hydrogen here. So here I have 4 hydrogen. Here I have 14. I need 10 more hydrogen. So I'm going to have to get it from the water. So that's going to be 5. So I have 5 times 2 is 10 plus the 4 that I have here. So that's 14. So I have 14 hydrogens and I have 14 hydrogens. Okay, good. My hydrogens are now balanced. Whew. Okay, so now back to the oxygen. So I had 24 here, 24 here. So I have 48 oxygen on this side. And I have 8 plus 16. That comes from the hydrogen. So 8 oxygen from this formula, 16 oxygen from this formula, and 16 from this formula, and 5 times 1 is 5. That gives me 5 from this formula. So when I add these together, 16 plus 16 is 32. 32 plus 8 is 40. 40 plus 5 is 45. So I'm missing 3. Let me double check here. So I have 3. 3 times 4 is 12 times 2 is 24. 8 times 3 is 24, so that's 48. So let's see here. my oxygens. So I have 1 times 4 times 2 is 8. 4 times 4 is 16. 8 times 2 is 16. And I have 5 times 1, that's 5. So that's correct. So I have 45. I figured out my problem. So this was not 6 for the hydrogen. If I go back to the hydrogen, I miscounted my hydrogen. So it should be 3 times 2, which is 6 times 2 is 12. So I have 12 hydrogens on this side, right? And so 8, that's going to give 8 on this side. So plus 8 gives me 20. And so on this side, 20. So here, I need 20. So here, so I have 4 on this side. I need 16. So this is going to be an 8. So 8 times 2 is 16 plus the 4 is 20. So now my hydrogens are balanced, which means that now I have, instead of 45, I have 48. So now I have my balanced equation. Sorry about that. So as you can see, sometimes you have to go back and forth and double check to make sure that you have the right number. So now we have this balanced equation. And so I hope this is helpful. I hope you now have a better idea of how to attack these sorts of problems where they give you the equation in words and you have to translate that into formulas and balanced equations. So I hope you found this video interesting and helpful. If you did, then please like, share, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any question or a problem that you need help with, or if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.